BAIS Class 3410, Enterprise Switching, Lab 3. Security within a switched network. Due March 23rd, 2018. Prepared by Ryan Matthews, Colton Rumbolt, Stefan Susi, and Amika Uche. Prepared for John Berlowitz. The purpose of this lab will be to expand upon the network we have built in our previous lab, but to instead implement various security measures to better protect our network against various forms of attack. We will also be configuring service level agreements, or SLAs, to monitor and respond to changes that we are experiencing in the network. Essentially, this lab focuses on how the network reacts and responds to the introduction of different simulated events. In the first section of this video, we will be going over the security measures that we incorporated into our IPv4 network to better protect against potential threats. In the first part of the section, we will go over the topic of port security. Port security is used to restrict the port access of a switch based on the MAC address of the connecting devices. But why do we use port security? Every switch has a content addressable memory table, or CAM table, which is used to make forwarding decisions at layer 2. Attackers will try and perform a MAC flooding attempt, where they plan to fill up all the entries within the CAM table, so once the CAM table becomes full, the switch has no other choice but to flood all traffic it receives out all ports. This flooded traffic makes its way to the attacker, where they can then intercept this data and use it however they wish. Port security prevents this type of attack by restricting the number of allowed MAC addresses that can be associated to each port, and then defines the type of violation action to be taken if a port detects is experiencing some form of MAC address attack. Before we show off our testing for port security, we just want to show what the CAM table looks like on the switch. We can view this by using the command show MAC address table. On screen, we can see all the different MAC addresses learned by the switch and which ports that they are associated to. Most CAM tables can only hold between 1024 and 16,000 entries, and it only takes up to 70 seconds for most MAC flooding applications to completely fill up this CAM table. Now, let's explore how we set up port security on a switch. To enable port security on a switch, we must first select the interface or range of interfaces we want to apply port security to. These are typically access ports. Once in the interface configuration panel, we use the command switchport port security to turn on our port security. Afterwards, we set the maximum number of allowed MAC addresses on that port. In this case, we chose to use 4. We can now proceed to specify what type of port security we plan to put on each interface. The standard command switchport port security to turn on port security automatically sets the port into dynamic mode, where it reads the traffic going through the switch and builds its CAM table accordingly. However, this CAM table data is lost whenever the switch reboots, making it not the best option for our choice in port security. If we add the option MAC address to the end of the command, this will allow us to set static MAC addresses on the port for our CAM table. This is also not the most desirable option that we have available, unless we know the exact MAC addresses we are expecting to see on each port, which is a very unlikely scenario in most networks. Lastly, we have the sticky configuration. This way, MAC addresses will still be learned dynamically, however, these entries are saved into the switch's running config, meaning the CAM table will not have to be rebuilt in the event that the switch has to be rebooted. There are also 3 types of violation actions that we can apply to each of these recently configured ports. The first mode available is the protect mode. This drops all traffic on the port if it detects that the MAC address connected to that port is not within the CAM table. Protect mode does not generate any violation errors if this does occur. The next mode that is available is the restrict mode. What this does is it also drops the traffic if it detects that the MAC address connected to a port is not within its MAC address table, but it will also send an SNMP trap message to an SNMP server when the violation is flagged. The last mode that is available is the shutdown mode. If a port with this mode receives any traffic that is not allowed, it will place the port in an error disabled state, which will then block all the traffic on the port, send an SNMP trap message, and will log a violation entry. To fix a port in the error disabled state, you'll need to forcefully shut down the interface and then re-enable it. To check all the port security information on your switch, you can simply use the command show port security to view all the important information that you will need. This includes each port, the max number of addresses that are allowed on each port, the current number of addresses learned on each port, as well as the number of security violations, and the security action to be taken if a violation does occur. Here's our switch and PC configuration for one of our legitimate machines on the network. We can see that the switch has a MAC address entry for a device that ends in E968, which also matches the entry on our host. To test for connectivity, our switch can still ping the default gateway, meaning that traffic is currently passing through the switch port with no form of violation. Lastly, when looking at the port security information on the switch, we can see that the max amount of MAC addresses has been learned and that the port is set to a shutdown state. We are now going to connect a rogue device to this port and view the violation that is triggered. On our rogue device, we can see that it has a MAC address that ends in 776A, meaning it does not match any of the port security entries that we have on the switch's FA01 interface. After we connect the device to the switch and the switch interface comes back up from changing the connected device, we can see that the switch triggers some syslog errors that show the port has been placed into an error-disabled state. If we observe our rogue device, we can see that it cannot ping the default gateway or any of the other devices on our network, and we will also see that there is a violation trigger set to 1 when we view our port security information. This means that we have successfully prevented a rogue device from connecting to that switch port on our network. If we reconnect our legitimate host, we will see that it is unable to ping the default gateway and other devices in our network. This is because of the shutdown violation triggered by our rogue device, which then placed our port into the error-disabled state. As mentioned earlier, to remove the port from being in the error-disabled state, we need to shut down and re-enable the interface for the violation to be cleared. Once the violation has been cleared, our legitimate host will now be able to ping the other devices on our network. In the second part of this section, we are going to discuss DHCP snooping. DHCP snooping prevents malicious devices on the network from impersonating legitimate DHCP servers and handing out false address information to the devices on our network. It is capable of doing this by specifying which ports are capable of sending specific DHCP messages. By default, all ports on a switch with DHCP snooping enabled will be configured as untrusted, meaning that they can only send DHCP discover and request packets. If the port detects the device sending a DHCP offer or acknowledgement packet, it will then shut the port down. However, ports configured as trusted will indicate that they can transmit all types of DHCP messages and that it leads to devices that have DHCP enabled that we are willing to trust for our addressing information. But how do we configure DHCP snooping on our network? When looking at our network, we only need to configure DHCP snooping on our access layer switches. Ports labeled with a red circle indicate that they are access links connected to end devices, and thus we do not want them sending any DHCP offers on our network. Ports with green circles indicate that they are trunk links configured to be in the trusted mode, as they lead to where our DHCP servers are located in the distribution and core layers of our network. Configuring DHCP snooping on the switch is rather simple. To enable DHCP snooping, we only need to use the command IP DHCP snooping. This will then configure all the ports on the switch into the untrusted mode. Next, we want to specify which VLANs we want to enable DHCP snooping on for our interfaces. As we are using SW-1, we do this for VLANs 5 and 10. Because all of the ports on the switch are already configured as untrusted, we only need to configure our trunk links on the switch to be in the trusted DHCP snooping mode. This can be done by entering the interface on the switch and using the command IP DHCP snooping trust. And that there is all we need to configure DHCP snooping on our devices. If we want to verify our configuration information, we can use the command show IP DHCP snooping to view the various information on the switch. This can be used to provide us information such as which VLANs the IP DHCP snooping is enabled on, as well as seeing which ports are configured as trusted in one simple show command. At this point, we would do a demonstration of showing that IP DHCP snooping working. However, on our network, we are having a hard time simulating the effects of having a rogue DHCP server on our network. So until then, we're just going to skip forward to the next part of this section. In this section, we will go over IP source guard. IP source guard is similar to DHCP snooping, but instead prevents attacks where a host tries to impersonate the IP address or MAC address of a neighboring device on the network. IP source guard does this by building a binding table which maps the DHCP assigned IP addresses to the device's MAC address, meaning if a rogue device tries to copy a device's IP, its MAC address won't match the entry in the binding table and it will then have all of its traffic dropped. It also uses a untrusted/trusted port dynamic where untrusted ports will filter its traffic via the IP source binding table, while trusted ports will allow all traffic. IP source guard will rely on the untrusted/trusted settings that we used in DHCP snooping, as it is a requirement to use IP source guard. Now, how do we configure IP source guard? To configure IP source guard, all we need to do is go to the trusted interface and use either IP verify source to filter our entries by IP, or to instead use IP verify source port security to filter our results by both IP and MAC address. We can view our IP source binding table with the command show IP verify source. This will then display the MAC address and IP bindings that have been assigned to each interface on our switch. For this test, we have a device configured on interface Fast Ethernet 0/3 that will try and attempt to copy the IP address of the device on Fast Ethernet 0/1. This device on interface Fast Ethernet 0/3 does have a current DHCP address ending in .52 and is capable of pinging our default gateway and other devices on our network. Once we try and change the IP address to mimic the device on Fast Ethernet 0/1 with an IP ending in .51, we will see that the DHCP snooping errors will show up and that we are unable to communicate with the devices on our network and generate a bunch of errors. The reason this occurs is because the IP source binding table detects that the IP no longer matches the one it has in its table and assumes that the device is trying to change its IP to something else on the network, thus trying to block all traffic from leaving the port. If we were to go back to our switch and search the IP source binding table, we will find that on interface Fast Ethernet 0/3 that the filter is set to deny all traffic on that port, meaning that our IP source guard is working correctly. To test and see if the MAC address filtering portion of IP source guard is working, we connected our rogue device to Fast Ethernet 0/1 and changed its IP to an address ending in .51. The binding table shows that the value of E968 is applied to the interface, but our rogue device has a MAC ending in 776A, which should then prompt the MAC filtering error. For this test, we also made sure to remove any and all port security just so that we know that port security isn't playing a factor in the reason why our traffic is being denied on the port. When we now try and ping the default gateway from our rogue device, we will see that none of the traffic is capable of going out to our network because it has failed the MAC filtering rule on the untrusted port. In this last section, we will discuss the topic of dynamic ARP inspection, or DAI. DAI prevents against ARP spoofing attacks on the network, where an attacking device tries to respond to ARP requests by providing its own MAC address in the hopes that a client will send all of its traffic to them instead of the original target. DAI prevents this by using untrusted/trusted ports to validate the MAC to IP bindings for all ARP requests from the DHCP snooping binding table. Only untrusted interfaces from our access links will need to go through these ARP inspections, while trusted links allow all traffic. We will now explore how to configure DAI and examine how it operates in our network. To configure DAI, all we need to do is specify which VLANs that we would like to have DAI working on. We will use the command IP-ARP inspection VLAN 5 and 10 for this switch, as those are the only VLANs that we will be using. Next, all the ports will be configured as untrusted by default for DAI, so we need to configure our trunk links to act as trusted ports. This can be done by using the command IP-ARP inspection trust. If we need to check to see which interfaces are trusted and untrusted, we can use the command IP-ARP inspection interfaces, which will then pull up a listing of all the ports on the switch and which mode that they are configured in. As mentioned earlier, the DHCP binding table will be used to show how we validate our ARP requests within our network, which we can use by viewing the show IP DHCP snooping binding command. Here is where the DHCP addresses are assigned to the host and where they are then bound to the MAC address on each device. If a device responds to an ARP request and it does not match any of the entries within this DHCP snooping binding table, the ARP response will not be sent to the client. For our test, we create a rogue device that will attempt to imitate the IP address of 172.16.5.52. This device will have a different MAC address than what is shown in the DHCP snooping table. The table has a MAC address entry of 776A, while our rogue device has a MAC address of 398C. We will flush the ARP cache on our primary client and see what kind of ARP responses that it receives. On our legitimate machine, we have cleared its ARP cache and have shown that it does not know any ARP entries within the network currently. When we try and ping .52 to start an ARP request asking for which MAC address is associated to that IP, our Wireshark capture is displaying that only ARP requests are being sent by our client with no ARP responses being received. This is because all the ARP responses from our rogue machine are being dropped by the switch. We know our ARP inspection is working, as when we connect to the switch, we can see that multiple syslog errors are being generated, indicating that the rogue device is generating invalid ARP responses. This concludes this section of the video. In section 2 of this video, we will be covering some of the IP version 6 security measures that we implemented into our network. First, we will explore IPv6 snooping. IPv6 snooping prevents the impersonation of neighboring IPv6 devices on the network as it builds an association between the MAC and IPv6 address. This functions similar to how IP Source Guard worked in IP version 4, but is instead used in a version 6 network. To enable IPv6 snooping, we first need to create a snooping policy. On screen, we created a snooping policy that limits the amount of learn addresses to 4, which is similar to what we did when we configured IPv4 port security. We then continued to apply this policy to all of our access ports that connect to our end devices. At this point, IPv6 snooping has now been fully configured. For our test of IPv6 snooping, we had 2 machines configured to use the same IPv6 address that ends in 4D15, but both devices will have different MAC addresses. Our legitimate client will have a MAC address that ends in 4F60, while our rogue device will have a MAC that ends in ED88. As we can see in the left control window, whenever the rogue device tries to ping the default gateway, it is met with constant request timeouts. If we go back to our legitimate device, if we try and ping the default gateway, we can see that all of our ping attempts are successful. When we look at our switch and use the show IPv6 neighbor binding command, we can see that the legitimate machine's MAC of 4F60 is mapped to the IPv6 address ending in 4D15, which means that our IPv6 snooping works. For this part of the section, we were going to show how IPv6 RA guard would be implemented. However, we cannot implement it into our network. IPv6 RA guard is not compatible with the Ether channels that we use to connect our access and distribution layers, so unfortunately we cannot include it in our lab. Instead, we will just discuss what its purpose is within our network. IPv6 RA guard would be used to prevent rogue routers on our network from sending router advertisements to our clients. We would specify which trusted interfaces that we would want to transmit router advertisements from, and leave either unused or access ports as untrusted. That pretty much covers IPv6 RA guard. Unfortunately for this next part, we also ran into the same issue, where we cannot implement DHCP v6 guard into our network due to the fact that we mostly used Ether channels to connect our access and distribution layers. Essentially, DHCP v6 guard would prevent rogue DHCP servers from handing out their own IPv6 address information to the devices on our network. It functions very similarly to DHCP snooping for IPv4, but is instead meant for an IP version 6 network. And that wraps up what DHCP v6 guard would be used for in our network. In the final section of this video, we will discuss how we configured a service level agreement known as an SLA to prevent traffic from being forwarded across our network in the event that our loopback gateway is unavailable. First, we configured a loopback interface on our core router and gave it an address of 10.0.0.10. For this demonstration, we will pretend that this is the link to the internet. We can see that on our switch that if we show the current IP routes, that there is an entry that defines the default route to connect to the loopback IP of 10.0.0.10. If we shut down this loopback interface on our router, we will notice that we will be no longer able to ping it, meaning that the traffic is not going across our network in order to reach the router, which is what our SLA was configured to do. If we pull up and look at the routes on our switch, we will now see that our default route is going to the null 0 interface, showing that it's no longer connected to 10.0.0.10. Once the interface is turned back on, we will notice that we can now ping the loopback interface from our client, and that we will see a change in the routing table that the default route will now go to the loopback IP that we configured earlier. To configure the SLA, we first need to create an SLA object for IPv4 and then start the object. It is set to check the availability of the default route interface at an interval of 10 seconds. We then also create a track object, which then uses our SLA with the commands to see if it is reachable. We then configure our default routes on the switch. 2 default routes are configured where the first route will have a lower administrative distance. Lastly, we also configure a schedule so that if the tracking object loses connection to the interface which represents our internet connection on the router, it will drop it from the routing table. This makes our statically configured route more dynamic. Once this route is dropped, our second static route will take over and drop all externally bound traffic. This covers our SLA that we configured for IPv4 network, but unfortunately, the switches we used did not support tracking with IPv6, so we cannot configure our SLA for our IPv6 network. This covers our section on SLAs. This is the conclusion of our video. We would like to thank you for taking the time to watch it, and we hope that we were able to teach you a thing or two about switch security. Until next time, see you then.